Monday was looking at your carbocations. Right? And one of the things that we added to our list up at the top is that, yes, the zero area are less, whoops, so I started to draw the thing the wrong way, are less stable than primary, less stable than secondary, and tertiary being the most. Right? While that order is true, the zero area and the primary are usually so unstable they don't form. Right? And so what students tend to then just memorize is, well, that tertiary is always best for a carbocation. Right? That's not true. Tertiary is better than secondary, which is better than primary and better than zero area. But no matter what you do with a tertiary, the carbon is always a positive 1 charge. Right? If we move to, say, a primary carbocation, but we now have a resonance effect, the carbon that carries the positive charge is now effectively half as large because that resonance reduces the charge on it. That means when we go through and look at our ranking, primary with resonance is going to be more stable than tertiary. Secondary with resonance is more stable than primary, and so forth. Right? The next part that comes out of it is if we run a reaction that forms a carbocation. Right? Typically, the lowest order carbocation we'd see would be our secondary. So if we see a secondary carbocation, we should immediately be thinking, is a rearrangement possible? Is it possible to move the electrons from within the structure to result in a more stable intermediate? Okay? Moving electrons on its own would be resonance. Rearrangements is taking this a step further. What we are moving is sigma bonds. Okay? That means we literally have to have a group or atom break away from the structure and change locations. That means you actively have a negatively charged species floating through space. Well, negatively charged species are not stable, which means your rearrangements happen in only very short distances. Right? So if we were going to draw out our structure at the bottom with our example, let's add a little bit more. Let's make that 1 an extra carbon. That red bond is now too far away to shift. Okay? But the one that I've got labeled as shift can. Okay? And that's what we're attempting to show with that product. Okay? Notice the arrow is starting where the electrons are located, which is the bond. And they are then going to the carbon atom of the carbocation. So we have to be very careful with where our arrows are starting and aiming. Okay? You'll notice also I drop a little curlicue in it. And that's because for me personally, once someone showed me this, right, I feel it is nice to draw a little bit more attention to the rearrangement than just a standard mechanistic arrow. Okay? That is a non-standard format to show the little curlicue in it. It's just an extra little way to kind of draw attention and say, hey, pay attention, you're doing a rearrangement, instead of saying normal electron motion.
Is that supposed to be a red line and then a purple line?
Yeah, it's a red line and a purple line, which we're going to look at here in a second.
Oh, I was just thinking.
That red line will lay stuff over the top, which should help out, right?
Thank you.
Okay, and I'm not writing purple, sorry. That's too many letters. Okay. If we went through and looked at that, the red line will never do the shift. Okay, we will never see that bond jump locations. Okay. Well, we said the shift atom bond could. How about the purple bond? Can that do a shift? Okay. Too difficult, fair enough. Switch it to the 2 bond. Is the 2 allowed to shift? Why are you saying yes? It's a sigma bond. It's the same distance away as the shift one. So cool. That's allowed to happen, right? Can the purple one shift? Yes. It is the exact same distance away from that carbocation as the shift bond is and as the 2 bond is. Really, but it looks like it's on the complete opposite side. I don't care what it looks like. What you have to recognize is the 3-dimensional characteristics of this. That carbon is sp3 hybridized. We have a tetrahedral structure. Right? If the shift atom is my wrist, okay, the shift location, that's my carbocation, my what is that, middle finger, is the same distance from that as my index finger, as is my thumb. But if I were to draw them out, what happens? My middle finger and the thumb look like they're closer. And my index finger looks like it's in the wrong spot. Does that make sense? So one of the things that we really have to process is that three-dimensional characteristic that gets in the way, and we talked about it in both Unit 1 and in Unit 2, okay, with those structural representations. We have to realize the bond angles, those shapes, all have a three-dimensional characteristic. The distance can seem far when actuality it's very, very close. Okay, so be careful when you look at structures. Kind of make sense? Okay. Well, what does the shift thing have to be? Let's just say we stick with the shift atom. It could be a hydrogen. Okay. What would happen if that was a hydrogen? Okay, well, what we're saying at that point is that position 1 and position 2 are carbons, so that if we go through this shift, what happens? I'm moving from a secondary carbocation to a tertiary carbocation. Okay? I've done a more stable, or generated a more stable structure with that hydride shift, so everything is golden. Okay? There was another suggestion. It could be a CH3. What's shifting now? The whole carbon. Right? What else could shift? Well, nothing. It's clearly just hydrogens and methyls, because that's all the textbook talked about. So this doesn't shift then. No, it does. You've got to be careful with that erasing. Right? Shift. Careful. Erasing. I can shift an ethyl group. I can shift a propyl group. I can shift an aromatic ring. Literally, I can shift any piece I want so long as I generate a more stable carbocation. Are you okay there? No, I thought you were just... No, okay. Nothing. Yeah. Okay. As long as I generate a more stable carbocation, it's fair game. I'm allowed to do it. Okay? That shift may be tertiary. It may be primary with resonance. It may be secondary with resonance. You have to be considering the order of stability for our carbocations for each of those shifts. Kind of make sense? Okay. So, let's take a look at this reaction. So we're still in chapter 8, so there's a really big hint on what you should be doing for this reaction. What is that really big hint? Okay, there's two really big hints. Number one, it says in big bold letters, we're going to be doing a carbocation rearrangement. As soon as we see the word carbocation, we should also be triggering in the back of our head a unimolecular type reaction. So it could be E1 or SN1. How do I know I want SN1? Because it says SN1. Right? And you're like, well, that was obvious. Start doing the homework and then tell me it's obvious. Okay? It is very easy to miss that extra information. If you've got a highlighter, highlight it on the exam. Okay? Because you will be seeing questions where it says, do this as an SN1. And you look at the reaction and go, oh, I think SN2 makes sense. I don't care if SN2 makes sense. It says do it as SN1. Okay? So make sure you read the question carefully and follow what it asks for. So under SN1 conditions, what do we do as our first step? The leaving group must leave. Where in that structure do I have a leaving group? The iodine is our best leaving group, because if iodine takes the electrons, it would become the most stable piece, I minus. Why did I not have oxygen take the electrons away from hydrogen? Well, isn't oxygen then acting as a leaving group? Because it's leaving hydrogen.
No, because they'll come back together.
Why would they come back together?
Because it's each proton in the
O minus is not a stable leaving group. Okay? I minus is the more stable leaving group. Okay? The other thing that we can consider within this, leaving groups are attached to our substrates. And because this is OChem, our substrates always have carbons in them. Okay? So with given two structures, we know the carbon structure is our substrate. The iodine must act as our leaving group. So let's have those electrons leave with the iodine. What is the result? Let's try and draw it exactly as they've got it. Okay. We've now formed a carbocation. The instant you see a carbocation, the question becomes, can I do a rearrangement? Well, what kind of carbocation am I starting with? I have a secondary carbocation. Okay. So let's try and do a rearrangement. What if I did that methyl? Because I'm allowed to do methyl shifts, so let's shift that methyl. What would the result be? Okay, well, I stabilized the carbocation at that one position, and instead, I now have a carbocation at the other. What kind of carbocation is that? Secondary. So is that shift allowed? No. It has to become more stable. Okay. If we add an extra layer on top of that, let's just say for giggles it happened. What is the relationship between the resulting product of that rearrangement and the starting?
exactly the same.
They're exactly the same. Okay? So no rearrangement, there's no difference, there's no reason to look at that. Okay? So that was a bad arrow. Okay? It happens. How about the other one? We're going to get the same issue. It's a secondary to a secondary. That doesn't help. Well, then that means there's no rearrangements. Because I've moved everything I possibly could. No?
There's an applied hydrogen on the carbon.
That carbon has only 3 bonds shown, which means there's an implied hydrogen there. Remember how we said back in Unit 1, watch out for implied hydrogens? Rearrangements is a big place where those will bite you. Okay? So watch out for them. If I do that rearrangement, what happens? We'll first draw it like this and we'll start to complain about it. We'll act like smart work and complain about our structure.
That's tertiary.
I would now have a tertiary carbocation where I started with a secondary. That is now more stable. That is more likely to occur. If I entered that into the little magic box for smart work, it tells me I'm wrong. But I did the rearrangement, smart work. I have to be right. Why am I wrong? I still have the positive charge there, though. Right? Or are you saying there's another positive charge somewhere?
Oh, well, that's why I put that in the.
Oh, because you showed
The electrons.
you showed one hydrogen, but if you show a hydrogen, you have to show both hydrogens.
This is I'm not quite sure to call it a feature or a flaw, okay? Because it has some utility behind it. If we look at that carbon where the hydrogen's connected, or where I've shown that hydrogen, I'm only showing 3 groups of electrons. Okay? Well, according to our rules, that means we have implied hydrogens. But you didn't imply that one. So what does smart work then assume? You're not implying hydrogens. Which then means that structure is wrong. It's either missing a carbocation or it's missing an implied hydrogen. So what does smart work expect you to draw then? You could draw the other hydrogen. Does that mean you have to draw the hydrogen on every other atom that has hydrogens?
Yes.
No. Really? No, it does not ask you to do that. Once you've specified one, you must specify it on that carbon. But let's take a look at that bond down there. Okay, for those of you at home, sorry, deal with me pointing like this. Okay, show up to class. What is that atom?
Carbon.
How do you know it's a carbon?
Point.
It's a point. All points are defined as carbons. Okay? How many electrons are currently around it
8,
that you see?
2.
2, which means there's an implied 3 hydrogens connected to it. I don't have to specify those hydrogens because everything is implied there. What if instead I write it now as this? Well, now SmartWork loses its mind. Okay, why? You've shown an atom C. So you're saying, oh, I don't want to imply things. Okay? Because you're now saying you don't want to imply things, what do you have to show? Now you have to show all the hydrogens connected to it. Do you have to show the hydrogen bonds? No, there's a handy dandy little, I think it's a hydrogen up arrow thing. You can click that button and then just click on the carbon. It'll go CH. Well, that's not enough, so you click it again and it goes to CH2. Well, that's still not enough. You click it again and it goes to CH3. Click it again, it goes to CH4. That's bad. Undo. Okay? Make sense? Okay. Did you have to show the purple and black hydrogens shown on the structure? That CH3 is bothering me. I want to get rid of it. Did I have to show those hydrogens? No. I could have just erased those entirely. Now both of them are implied. That's a fair answer. Okay? But once you specify one, you must specify the other. This is one of the issues that students encounter. We just shifted a hydrogen atom. Okay? A hydrogen atom that you couldn't see, so you drew it in. Now you see it. What do you want to do in the product? You likely want to see it, which is fair game to now show it. But if you show it, make sure you specify all the hydrogens there. Okay? Is it necessary to show those hydrogens? No. Because it is not necessary, guess what happens on, say, a multiple choice test? They're not shown. So you may think that you haven't done a rearrangement because the hydrogens weren't shown. They aren't required to be shown. Okay, so you have to be careful with rearrangements. You may have to add a hydrogen so that you can see the rearrangement, but then you may very well not show that that hydrogen was even there in your product. Make sense? All right. So now what happens? Tertiary carbocation. Can it become more stable as a carbocation? No. So now what happens?
The electrons from the oxygen coming in.
Something needs to permanently stabilize that positive charge. I have to find electrons from somewhere. Where are those electrons found? Okay. In my water. So this is where the lone pairs can help. The lone pairs come in and share the resulting structure. Would be with the oxygen attached. Great. Now what's wrong with that structure? I have a positive oxygen. How do I fix that? The oxygen will steal electrons from one of those hydrogens, and we end up with our final product with the OH attached. Before we're like, okay, fine, done, wash our hands of it, do we have a chiral atom? No. Okay, I don't have to worry about it then. If it was chiral, then I have to start worrying about it. Okay, but because it's not chiral, I don't have to worry because those CH3s are identical. Questions about anything that's shown up there? Yeah?
What's it say that the iodine there would go back and detach?
What prevents the iodide from attaching again? Okay, it has to do with the stability of it. Okay? So one of the things that we don't really address a lot in first semester is that virtually all of these reactions are reversible, at least to a certain extent. I mean, we have to deal with equilibrium concepts? Yes. Okay. Why does it end up reversing relatively minimally at later stages? And in fact, actually here, okay, the secondary to tertiary is not reversible because the secondary is less stable. So that one is unidirectional. It only goes towards the tertiary. Okay? So why would I end up having the water attack instead of the iodide? The iodide ends up being more stable on its own than even the water, which allows for the water to come in and directly connect up. Okay? Some of it can also come into concentration amounts. If I have a crap ton of water, the chances that iodide encounters the carbocation, next to nothing. What's the issue with concentrations? Where in that equation does it show anything about concentration? It doesn't. Okay? So a lot of that kind of concentration information becomes implied behind this.
So where did that second hydrogen go? In the product, it would be just as
I just noticed that too, because I asked the question about concentration. Okay, concentration is an amount per volume. Well, we don't see that here, but do we see something about an amount of either of our starting materials?
Yeah, 2 waters.
It says I need 2 waters. Okay, so what picked up that hydrogen? Well, something with electrons. Would iodide pick up that hydrogen? Why not?
Yes, it would, but it will dissociate immediately.
Iodide will not pick it up because it dissociates immediately. So it makes no sense to have the iodide pick up the hydrogen. Why does it dissociate immediately? Somebody else. Somebody else. HI is a strong acid. By definition, it completely dissociates. I only had to silence it because I knew you knew the answer. All right. It's a strong acid. So that's not allowed to form. So what then picks up that hydrogen? Well, another source of electrons. What's our other source of electrons? We have a second molecule of water, which conveniently in this case they told us was present. That comes in and picks that up. The other product we'd also be drawing out if we were forced to draw all the products, which is super rare, but sometimes it happens, would be H3O+. Because you know in theory that I've been doing OChem for a little while, at least I hope it comes across like that, why did I not show this purple structure? That's also a product, right? It's not organic. I don't care. Gone. I don't even see it. Disappears. I keep my focus on the organic molecule. Why did I not show water pick up that hydrogen? How easy are acid-base reactions? They're easy. How do we know they're easy? What were the reactions you learned in Gen Chem? Acid-base. How many of you learned substitution reactions in Gen Chem? Oh, you didn't. Why not? Because that crap's hard. Acid-base is easy. Acid-base is such a very, very fast, facile reaction. There's a $5 word for you. Maybe, yeah, I think that's even better. 5-letter word for you. 6-letter word for you. That I don't care about what species is picking up that hydrogen. Okay?
Would the hydronium pick up the iodide?
We could then push out, well, where does that iodide float out? Well, the iodide needs to get stabilized somehow. It will probably interact fairly strongly with the hydronium. Why? The negative positive charge. Again, OChem, I don't care. I care about that species.
So for the final product with the OH bond, is there two sets of lone pairs on oxygen?
So another good question. Shouldn't there be 2 lone pairs on the oxygen? Yes. What can I do with those? I can imply those. So it's good that you call me out on it because I shouldn't be implying them right now because we need to practice recognizing and seeing them. Okay? Those lone pairs are there and they are superly common. Superly? You should call me out on that instead of less good. Less good, by the way, is linguistically correct. Because you aren't as comfortable with it. If we go all the way back to Unit 1, I said the abbreviations, the common implications. Heteroatoms, anything not carbon or hydrogen, we very often imply the lone pairs. So you are responsible for knowing that. You may not be constantly aware of it, so I should be trying to show them for you. Okay. Other questions about what's shown up there? You guys covered all the questions I was going to ask you back, so I guess that's good. Okay. So there would be our product. Is that product different than what I showed you? You're like, I don't remember what you showed me. Yeah, I know. I just deleted it. So let's draw it again. This is what I drew. Are those two products different? Why not? There's no stereochemistry. It's a tetrahedral carbon. All it is a different rotation of that bond. Because that rotation changed, that just made it look like the OH has changed locations. It's still connected. This atom connectivity is the same thing. We have identical structures. Okay. Yes, you're responsible for knowing that. That's why we went through those comparisons back in Unit 2. Okay? So, that was our big repercussions for our SN1. So in the SN1, we had the carbocation being a rearrangement, which we just spent a lot of time about. And the previous one on Monday that we talked about for a complication in the SN1 was 2 products coming out of that, largely again because of the carbocation. All right? In the SN2, we get another repercussion coming on with this. We don't have an intermediate, so I don't have to worry about rearrangements because there's no intermediate to rearrange. Okay? I also don't have to worry about 2 products because the orbital that's reacting is an anti-bonding orbital on the back side of the carbon chlorine. Okay? Don't stress about the words, just mean it's on the back side. Okay? So there's only one place the nucleophile can attack. It has to attack from the back side. Okay? And because it has to attack from the back side, being only one attack, how many products would I get? 1. Simple. So if I go through and draw out my product, I would get my 1 product with my iodide attached, and there's my chloride floating around. Just like we did with the SN1 on the previous slide, once we finish and say, now we've got our product, what should we evaluate? Do I have a stereocenter? I have a carbon with 4 different things attached. Okay? Oh crap. Do I have to worry about that? Okay? Well, the answer to that question is now, were you told anything about stereochemistry to begin with? Because if you weren't told anything about it to begin with, your answer to that is no, because we didn't care enough to ask it or provide it at the beginning. You don't have to worry about it at the end. Okay? Are we told stereochemistry at the beginning?
Yes.
Yes. Do I need to worry about it in the end?
Yes.
Yes. Okay? So now what happens? Well, remember that iodide is coming in from the back side of that carbon-chlorine bond. Okay, well, where is the carbon-chlorine bond as it is drawn? It's coming at you. What is the back side of coming at you? Going away. Which means, how should I draw the iodide in my product? I should draw it dashed. Right? Well, if it is dashed, what happens to everything else around there? Because if we look at our starting material, we had a methyl group that was dashed. Can I have 2 dashes? No. So what happens as that iodide comes in and attacks? It's going to force that methyl group forwards, making the methyl group wedged. Okay. One thing I want you to be cautious about with this. Most students will remember, okay, it's inversion of stereochemistry. So if it's wedged, it becomes dashed. If it's dashed, it becomes wedged. What if it's solid?
It stays solid.
It stays solid. Okay? So what you're saying is if I drew this structure out along these lines, chlorine, I'm not sure I'm drawing the same one, by the way, so no promises there. So you're saying if I now do this substitution with the iodide, then my product is now this guy. That's a ring. Stayed solid, right?
You can determine stereochemistry based on RMS.
Okay. It has to attack from the backside. Wedged and dashed are obvious. Because there's only one wedged, there's only one dashed. What happens if it's a solid line? Where's the backside of that carbon-chlorine bond? Wedged and dashed was easy, but the backside is going to be solid. It's going to be solid, though, coming up the other direction. So this answer doesn't quite make sense. Okay, so we're just going to put a big X through it for the moment. It was a horrible X, but you get the idea. And draw what we would get. We'd get the iodine coming up here, yeah? Well, what happens with the phenyl group and the methyl group? Well, if the iodine comes in from the backside, what are those two groups going to do? They're just going to move that way. Are they flipping? No. They're just moving down. Which means the result out of this is that I'm going to have my wedge now down to my phenyl. Notice I drew it better that time. And then there's my methyl, my CH3. Okay. It may look kind of ugly, and I could pretty that up if I wanted, particularly because I have an eraser. Okay. And there we go. Well, is that structure the same as what I drew in red? Okay. The iodine has to be solid, but it needs to be solid down. It's now currently solid up, so what I'm going to do is grab that iodine and I'm going to rotate about that sigma bond. Okay. I want to rotate there and get that iodine aimed down so that it's matching the general structure of the red. This methyl group was aimed up, right? Or aimed out you. In that rotation, okay, we're rotating it, we're pulling that iodine kind of backwards. What happens? It goes away from me. So the answer for that methyl should then be, or sorry, that phenyl should then be that. What happens to the methyl? The methyl becomes wedged. Are these two structures the same? No. What's the relationship? Enantiomers. Okay, they are mirror images of each other. Okay. So when you go through to do your SN2s, it's not just saying, oh, it just does the opposite. Oh, if it's solid, it stays solid. It's where those things are relative in space. Leaving groups on wedges and dashes are easy because it's either at you or away from you. It's very obvious which is opposite. The solids, because there's two solids, it's not quite as easy to determine. Okay? So on a multiple choice test, what could be given as the answer? I could say predict the product of this SN2 reaction. Well, I could give you the red structure. I could give you the black structure. I could even give you this other black structure. Okay? They all look pretty darn similar, right? Okay? And our instinct might be, well, the red one can't be right because it's in the same spot. Okay? The black one can't be right, or sorry, yeah, or maybe the black one can't be right because it's still solid. Okay? So what you'll end up doing is falling in this trap of now marking answers as wrong when they were right because you aren't paying attention to that spatial awareness. Okay? That is insanely difficult to track. Okay? But you're responsible for that. Okay? What is the relationship between the black one or the two black ones? You might say that bottom one was awesome because it looks like it's on the opposite end. But what if I only give you these two answers? Well, now when you look at it, you say, well, in fact, I'll even be extra obnoxious. We'll add a third answer. You're like, well, that's not that big. Where's the back side of the chlorine? Right out there. Well, the iodine, clearly not out there. The iodine, clearly not out there. It must be none of the above. God, all we did was a rotation. The answer becomes less obvious. So you have to be aware that your molecules can rotate. You have to take that into consideration when you look at your answers. Okay? Don't just jump and say, well, it's not immediately on the backside, so it has to be wrong. These structures can change their orientation, which changes your interpretation. Be very, very careful with that. Make sense? Okay. The way the textbook likes to describe it, and sometimes you'll hear instructors describe it, is this whole inversion with an umbrella. Sometimes that makes sense to me, sometimes it doesn't, so it's kind of hard to say. If we're looking at the umbrella, the leaving group is the point, the stabby end of your umbrella. Okay? And then it kind of shields down around you. Well, the shields down around you is the rest of your substituents. Okay? What happens when a gust of wind, like a nucleophile, comes in underneath? Okay? Well, that gust of wind now pushes all of those substituents and forces them the other way. And because that happens, now the cap to your umbrella goes, because that's the sound effect. It goes shooting off the other end. Okay? That's what they're trying to represent with the umbrella and that inversion. You will always get this kind of umbrella wind gust inversion effect. That does not necessarily mean you get an inversion of stereochemistry. Okay? Remember, the stereochemistry has to do with the substituent that you're trading. Or chlorine for iodide. The priority for chlorine or iodide in comparison to the carbons is the same. They're both higher priority. So we will expect a change in stereochemistry. But what if that nucleophile was also a carbon? Is that now going to change the potential result of my stereochemistry? It can. So we have to be careful when we go through to interpret to not just blanket statement say inversion. Okay? If you look at your nucleophile and you look at the pieces around and you're like, those look kind of similar in terms of priority, using, what's the famous word? 2 words? Kahn-Ingold pre-log rules. Take a look at exam 2. Okay? Your Kahn-Ingold pre-log rules, if your nucleophile and the remaining pieces, okay, have similar priorities, you may not necessarily see a full shift from S to R or R to S. Okay? It may very well maintain. It just depends on those priorities. Okay? You will still always get the umbrella flip. Okay? So now we can move into the E1, okay? And in particular, the visualizations of it, or repercussions of the E1. So the first repercussion of an E1 reaction is that it's an elimination reaction. And in an elimination reaction, what do I produce? A pi bond. So I'm already going to see a different product come out of this. Okay? Because it is a one-type, unimolecular, the rate determining step is going to be the leaving group leaving, just like for the SN1. So the first step for the E1 and the SN1 are identical. Okay? So the leaving group leaves, generating a carbocation. What is special about a carbocation? Where is the carbocation found on the carbon? On a p orbital. And a p orbital has lobes of space for electrons both above and below the plane of the molecule. Which means when I go through to do the elimination, the electrons from that hydrogen leaving can either come into the top lobe or the bottom lobe. So depending on the orientation of that hydrogen, I can potentially see different products come out of this. And that's what this slide is attempting to show, or this figure from the textbook is trying to show. So once we've formed that carbocation, first off, if I was to take a pen and put that pen on this structure, where's the carbocation? Where's the p orbital? Is it there? There you go. It's coming in and out of the board at you, which means to do the elimination, where does the hydrogen need to be? At you or away from you. Where is the hydrogen currently located? In the plane of the paper. So it's in a perpendicular orbital. It can't do the elimination yet, which is why, what do they tell you to do? They tell you to rotate that sigma bond. Okay? And in the bottom case, what have we done? We've rotated it so that the hydrogen is now coming at you so we can do the elimination. And in the top case, what happens? The hydrogen is now away from you so you can do the elimination. Okay? So all we're doing is doing elimination. We generate a pi bond. Why do I have to draw all these stupid things out? Okay? Well, what happens when I go through and do that? The instant I make that alignment, can I rotate that bond anymore? No. It's locked in place. Which means the relative location of the substituents are now also locked in place. Okay? So for this single starting material to run that elimination, I don't have a nucleophile attacking backside or same side of a p orbital, but I do have that hydrogen attacking two possible sides of that p orbital. And it turns out in this case, if I do the elimination, I can end up with those two rings being on opposite sides of the ring, or of the double bond, or same side of the double bond. Which means I could get cis or trans, ultimately the less fancy way, two products. Okay? So when I run an E1 elimination, just like with an SN1, I need to be concerned about the possibility for two products. Okay? So let's look at those two products and say, well, are they of equal energy? Because in our SN1, the reason we got those two products is they were equivalent in energy. Are both of these equivalent in energy? No. Okay. We have a cis double bond at the bottom, and we have a trans double bond up top. Based on what you remember from God knows what chapter, but one of those previous units that we looked in, I think unit 2, right? Which double bond is more stable? The trans, which means when I run the elimination reaction, how is the structure going to align to generate the product? It's going to align in such a way that I get the trans product. So while it is possible to get two products, the majority of my product will be the trans, okay? Because it is more stable. It's lower in energy than the cis. Okay? Well, how much more of the trans do I get than the cis? What's going to dictate that? It's really going to come down to looking at the cis and saying, well, how big are those groups? Are those groups really, really, really big and they're butting up against each other? Then yeah, don't do that. Are they smaller? Then it can probably happen. Okay? So a lot of that is dictated based on the size. So in this case, we're looking at 6 carbons in a ring with a bunch of pi bonds. What do you think? Really big or really small? Those are pretty big. Okay? Which would suggest I get a lot of the trans. And I get a relatively tiny amount of the cis. Okay? What if instead of being phenyl groups, they were now methyls, CH3s? Now we'll get a little bit more of the cis. The trans is still the more stable product, okay? But that ratio between those two products is going to change. Kind of make sense? Okay. So that's kind of a big deal with our elimination. Okay. I went through and spun it with the orbitals so that you can see the orbitals. Okay, so you can see my goofy drawings. It's the exact same thing as they've got set up, except instead of just showing the floating carbocation, I showed the p orbital and showed where the hydrogen is coming from to make that double bond. Okay, so it's a slightly different view of the same structure. Okay. The result is now going to force those same differentiations in products. Kind of make sense? Okay. Do we need to go through this slide in a little bit more detail than the previous one? Or are you guys okay with it? Yeah.
I just had a question on the last one. What was the ET next to like where the hydrogen was like, in the product?
Oh.
What does that stand for?
So the question is down with this guy. I'll make that a little bit bigger where there isn't writing. We have HO. The question is the ET. Yeah?
Is that just like bromine in this instance?
No. Because what would our symbol be for bromine?
BR.
Br. So I don't accept that. What would ET be? Ethyl for ethanol. It's the solvent. Okay? So you will oftentimes see alkane chains abbreviated because ET is apparently easier to write than if I had just written. So, I don't know, but that's the explanation behind it. Right? So the other common one you'll see would be ME. ME actually makes a lot of sense because that's methanol. But most people don't see that as a carbon. But if we write it out as HOME, now it stands out. So ME and ET are super common. ME for methyl, ET for ethyl. You'll sometimes see propyl show up. I think more often I've seen IPR, which would be isopropyl. Okay. Since we're in this conversation about stability, and we go through and look at this when we run this elimination, okay? So a new structure, new system, new problem. We form our carbocation, and we said we get two possible products, right? Trans and cis, depending on which hydrogen we removed. Okay? Which hydrogens are we talking about to make these? Talking about that hydrogen or that hydrogen. Because I don't have wedges and dashes on this, we'll just go through and just call this red and purple for just kind of the hell of it. Okay. Those hydrogens would be identical, but the elimination produces different products. Okay. So we'd have to be careful with that. Okay. Where are those hydrogens located with respect to the carbocation? Okay. There's someone that was in Monday lab, or paid attention to the lecture, textbook I mean. They're the next carbon over, right? So if I went through and numbered this as the first carbon, well, they would be at the second carbon. Okay. Before we get too excited about writing 1s and 2s down, what's the issue about writing 1s and 2s? Where's carbon number 1? It's not there. Carbon number 1 in nomenclature is actually one of our chains out at the end. Okay, so I can't use 1 and 2 because that doesn't make sense. So I would need a new numbering system that doesn't involve numbers. I could use A and B. Okay? That would make all too much sense if we spoke the English language. Let that one sink in. Okay? And instead we use Greek letters alpha and beta. So those hydrogens are located at the beta position to our carbocation. And our carbocation is then defined as our alpha position, okay, in this particular case. Okay? Which means when I go through and do this elimination reaction, what am I eliminating? I'm eliminating a hydrogen from the beta position. So instead of calling this an E1 or an E2, I could call this a beta elimination, because I'm eliminating from the beta position. Okay? So you might hear reference to beta elimination. That's all we're talking about. Okay? And we're referring to the hydrogens that are 1 carbon away. Are there other hydrogens that are 1 carbon away? Like down here? Yeah. I didn't talk about those, right? Why did I not try and remove those electrons? Because that's also a beta position. Would that result in a copy of one of those other products? No, we get a third product. Why did I not talk about that product, but I talked about the cis and the trans? Well, the cis and trans are clearly the more important product. But why are they the more important? Well, they're more stable than the blue one. Why are they more stable? There's more substituents attached to the carbons of the double bond in red and purple than there is in the blue. Okay, those are some fancy words. So let's identify the carbons of the double bond. Well, there's a carbon of a double bond. There's the other carbon of the double bond. How many non-hydrogen things are connected to those carbons? Well, there's 1, and there's 2. How many non-hydrogen things are connected to the other one? Well, 1 and 2. How about for the blue one? 1. Which is more stable? Okay. This goes back to the reactivity. What is the most reactive thing in all three of those structures? The pi bond. That's the highest energy electrons. Okay. For those electrons to react, they must leave the structure. Okay. Which means there should not be other electrons around them. Well, what did I put in the circles? Non-hydrogen things like carbon. And what does carbon have? Electrons. So for the pi bond to leave, it has to get around electrons. In the blue structure, it's only getting around one source of electrons. In the red and the purple, it has to get around two sources of electrons. Right? It's really easy to sneak out of the house if there's multiple exits to your house. Right? If there's only one exit, that becomes a little bit more difficult to sneak out of the house. Okay? No one has to sneak out of the house, presumably, anymore. Right? Maybe? Right? Who knows what you're doing with your personal life? Maybe you're actually fighting crime. That'd be cool. Okay? So what happens? The blue one is less likely to form. And it's the red and the purple ones that are more likely to form. Okay? This observation, okay, has to do with how the reaction occurs. And ultimately it ties all the way back to the Hammond postulate. You're going up in energy because you're making an alkene that's higher in energy. We want the most stable product to come out of these. The most stable product is going to be the most substituted. Okay? The hand-wavy argument is that it's just more difficult to react. There's more exits in the house. Okay? Or there's less exits in the house. Okay? If we drew it out as an energy diagram, yeah, okay. I started it. Might as well finish it. Okay? With our starting material, okay, there's our reactant. In all three cases, we would go up in energy to form the intermediate, because the intermediate's the same in all three cases. If I now had to draw on, let's do C. Where would C be? It's going to be the top one. This is going to be C. Okay. What happens with B? It's going to be the lowest. And A is in the middle. Why do I expect more of the B product? Okay. It was more stable. Well, why is that relevant? What about the energy diagram? The picture on the screen tells me that B is the more likely product. It's lower energy. So really what you're trying to say is that B is thermodynamically more favored. Because kinetically, they have all roughly the same energy. They have the same activation barrier. And if I go through and run this reaction with X amount of heat, I will form C. Okay? But what happens with C? It is more reactive. When it reacts, what happens? It will make a carbocation. It goes backwards. Why is C allowed to go backwards, but B not? What is the activation energy for B? The reverse process is now a massive activation energy, whereas for C, it's relatively tiny. What we're evaluating here is the concept of kinetics and thermodynamics. 152. Okay. Do you really want to worry about it? No? Okay, don't worry about it for this semester. It's going to be huge in second semester. Virtually everything we talk about is kinetics and thermodynamics. Okay? If you want to jumpstart over the summer, you can start watching some videos on kinetics and thermodynamics. It's exciting. Okay? Let's throw in one more kind of curve into this, because you've seen this already. You've been tested on it. Okay? We throw in our ranks here. We had what? C, A, B. We could also reference this concept of, what the? Sorry. Personal space and everything. Heat of hydration. What is heat of hydration talking about? And in fact, it shouldn't be written as heat of hydration. It should be written as the heat of hydrogenation. What are we talking about with the heat of hydrogenation? Hydrogen, yeah.
What it takes to put a hydrogen on it?
What happens when we put hydrogen on it? You mean get rid of the pi bond? Yeah, if we just add hydrogens to it. If we get rid of the pi bonds, we're now going to a lower energy. If we look at the heat of hydrogenation for B, what is our heat going to be? Well, it's the distance between those two. It's a relatively small value. What is the heat of hydrogenation for C? A much bigger value. Right? So the energy diagram can give us a concept of what's happening with the heat of hydrogenation. So when you see questions about heat of hydrogenation, the best way to do it is to look at an energy diagram. Okay? What should the sign be on the heat of hydrogenation, just to add salt to the wound from 152? Should it be positive or negative?
No, it's gonna take heat, but
Your product is lower in energy than your reactant. So if we look at the sign, product minus reactant, if your product is lower in energy, it's a negative. It's an exothermic reaction. It will release heat. Okay? It's a tricky one. I almost always screw it up. That's why I have to draw the energy diagram. Okay? So, your double bond substitution patterns, we've got tetra substituted because there's 4 things connected to the carbons of the double bond. Okay? Tri-substituted because 3 di, because we've got 2, 1 mono. Okay? The more substituted the double bond, the more stable. Interestingly enough, the elimination for reaction, or E1 eliminations, will always produce the more substituted double bond. Guess what happens for E2? The same thing. They're both resulting in pi bonds. We want that pi bond to be as stable as possible. So eliminations will always favor the most substituted double bond. Okay? The word that typically gets accepted with this, okay, is the major product of the reaction is the more substituted double bond. This gets colloquially referenced as Zaitsev's rule. Okay? Not a big fan of it because Zaitsev's rule does not actually say that. Okay? Zaitsev's rule is referencing the number of hydrogens. Okay? Why? Because when Zaitsev's rule came about, literally did not know what electrons and protons were. Okay? If you don't understand electrons and protons, you don't understand anything about energies of pi bonds. Okay? So he gets a lot of credit for this because it was his initial discovery to say that you get the more substituted double bond. Okay? But it really comes back to kind of archaic references. What you should be getting out of it is make the most substituted double bond. Okay? The fun thing that comes out of this, anybody kind of notice anything that might jump out at you of like, oh crap? Whenever you sign up for something, they give you the EULA. EULA? What's the EULA? The End User License Agreement. Okay? And you never read it. Why do you never read it? It's long and the font is insanely tiny. Okay? Why? Because they can hide lots of nasty things in there, like we can sell your personal information. Thank you, Facebook. Why might we be nervous about this slide? There's a massive little exception in tiny little font at the bottom of this. Okay? We can encounter something known as a Hoffman elimination. The Hoffman elimination will only happen for the E2 elimination. Okay? So if we're running through a carbocation, no Hoffman. Okay? The hydrogen must be sterically hindered. Okay? And we have to use a sterically hindered base. Okay? Well, we haven't talked about what E2 is yet, so we don't have to stress too much about that because all we've done is E1. Just realize there's an exception to Zaitsev's rule. So practice. Okay? There are 3 possible products. I will give you a minute and a half to draw those 3 possible products. So I asked for 3 possible products. How many of you drew any of these 3 structures? Wait, nobody did? Good. None of them are correct. Okay. We're doing an elimination reaction. Okay. All centered on the location of our carbocation. So if we go through and do our elimination, we have one option here. We have one option there, and we have one option there. Notice that those all have one position in common. That one position would be the starting carbocation. Right? So what we did was removed the hydrogens from the beta positions. There were 3 possibilities. Of those, which one is the favored product? The very first one is going to be our favorite product. Why? This one is tetra substituted. The next one is only di substituted. The last one is tri substituted. Okay? So we have to be considering all of those possibilities. Depending on the system you're looking at, you may see other things pop up. So you have to watch out and realize that maybe your first hydrogen that you see is not the one leading to your answer. Kind of make sense? Okay. So E2. So E2, we're doing an elimination. It's bimolecular, so now everything's happening at the exact same instant. So a lot of those rules that we just went through and talked about for E1 will still hold true. You want the most substituted double bond. Okay? But the next big thing that comes out of this has to do with it all happening at the exact same instant. Okay? What is the relationship between these 2 starting materials? Can't be cis and trans, there's no double bond. Okay. If we take a look at this position, we have 4 different things attached, right? Okay. Those 4 different things attached mean we have a stereocenter. Have they changed? No, so they stayed constant in between those 2. What happens at the other position? Okay. There's another stereocenter there because we have an implied hydrogen. Okay. And if we look at that position, did the stereochemistry stay the same? No, it changed. So what's the relationship between the 2 structures? They're diastereomers. Okay. So what does that mean our products should be? Careful. Diastereomers would assume we kept our stereocenters. If we're doing an elimination, what's going to happen to the stereocenters? We're probably going to get rid of the stereocenter because we have to make a pi bond. Okay. Would we expect the same product? No. What product do we get for the top one? The electrons come in, remove the hydrogen. Notice here I'm actually showing something remove the hydrogen as opposed to the last one. Why? What is different about this species than the previous one we looked at? This one is strong because it's negatively charged. Because it's strong, it's going to be active in the mechanism. I do want to show that. If it's not strong, I don't really care about it. Okay? A bull running at me versus a little kid. The bull's kind of stronger than the little kid. I'll probably worry about the bull. Okay? Those electrons need to come out to form the pi bond. Notice they're coming in from the backside of the leaving group bond. Okay? If we were to draw this really sloppily at first, we could go through and do this, wedge, dash, I'm going to do pH for that ring for the sake of time. Wedged pH dash, there's our hydrogen. The geometry about those carbons is trigonal planar, which means wedges and dashes are a horrible thing to show. So instead, I'm going to flatten those out. I'm going to say the wedged is down in front. So there's my CH3. There's my pH. The pH on the other side is wedged. It's still coming out at me. That would be my product. Everybody see it? If we go through and do the same thing with the other one, our base comes in, removes the hydrogen, kick out our leaving group. Now what happens with our product? We get the pHs being, or the phenols being, cis as opposed to trans. Okay? This gets more complicated, or can be made more complicated by doing a relatively simple adjustment to the structure. So let's just take a look at that bottom one. And this is what I'm going to do. What did I do? This was a rotation about the sigma bond. So I haven't changed anything inherent behind the structure. All I did was a rotation. Okay. Can the elimination proceed from this configuration? No. Why not? It's the 2 type. It has to be a backside attack. Okay. The hydrogen must be on the backside of the leaving group. Where's the backside of the leaving group? Well, the leaving group is in the plane of the paper, going down, which means the hydrogen needs to be in the plane of the paper going up. Is there a hydrogen there? No. No elimination happens in this conformation. Okay? Which is a tricky thing to watch out for. We'll talk about this in a little bit more detail on whatever it is, Monday. There's the prettiness behind it. Which gets extra pretty when you bring in Newman projections.
Can you go back a slide, Mike?
Yes.